Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to kind of mix the idea of equivalent resistance with Kirchhoff's laws in order to analyze a circuit. So in this picture right here, what we're looking at, we've got this 12-volt battery hooked to the following resistors: a 1 ohmer, a 2 ohmer, a 5, a 3, and a 4 in the configuration shown. And I'm going to go ahead and draw currents now. So there is going to be a current in this branch right here. And I'm going to give that current, except I'm going to go back to my black pen here. I'm going to call that current I1. The direction is dictated by the battery here, battery voltage. Remember, current always goes from plus to minus, or assuming positive charge carriers. At this point, there's going to be some divvying, so we're going to have currents here and here. I'm going to call that one I2, and then the current in this branch, I3. Right, these currents kind of come back together. At this point, we're going to have more divvying here, so we're going to have a current in this direction. I'm going to call that one I4, a current in this direction, I5. Now, one could argue that we have a current in this branch as well, but if we look at this, if I define a system like this right here, you'll notice that the only thing coming in is this current in this region, and going out is I1. So this current right here would be equal to I1. It's not going to show up anyway because there's no resistors anywhere in that part of the circuit, so I'm not even going to bother labeling it. All right, now, the one we're after here is this one. And I'm going to try to take you through one possible path to get that. Now, there's different ways to analyze circuits. One way is just brute force. I could just start writing equations. Right? So we've probably talked about in class now Kirchhoff's loop equations. One thing I could do is I could write a loop maybe like this. The equation for that loop, though, is going to have a bunch of unknowns. It's going to have an I1 unknown, an I2 unknown, and an I5 unknown. I could then maybe write another loop. That's going to have two unknowns, I2 and I3. I could write another loop. That's going to have unknowns, I5 and I4. Let's see, what are we up to here? I'm not even sure how many equations I've written, but I could write this loop, which is going to have unknowns I1, I3, and I5. I could also write some junction equations. At this junction right there, I could say that I1 is equal to I2 plus I3. At this junction, I could say that the current I1 coming into that junction is equal to I4 plus I5. So I could write a system of equations and solve for the 5 unknowns, and then I would have I2. But let me go back to one of those loop equations again, this one right here. If I knew the current I1 and perhaps I5, I'd have an equation that's with only one unknown here to get me I2. So that's kind of the game plan here. I'm going to simplify this circuit down. Then I'm going to try to find one or two currents and then look for a simple loop to get I2. So here's what that might look like. Right? All right, these two right here, they're in parallel. Pretty easy to calculate the equivalent for that. We would have 1 over R equivalent is going to equal 1 over 2 plus 1 over 5. And I usually just use a calculator when I'm doing these things. Remember, when you calculate the equivalent resistance, though, you have to remember to invert when you solve for this thing. So the equivalent of that pair right there, I get 1.43 ohms for the equivalent to that combination right there. Right? Now, this pair right here, we can find an equivalent for that pair by saying, let's see, 1 over R equivalent is going to equal 1 over 3 ohms plus 1 over 4 ohms. I should put note consistent units here if I'm going to leave them off. All right, so we have 1 over 3 plus 1 over 4 equals, and then invert it. Right, and I get 1.71 ohms for the equivalent of that pair. What this is going to allow me to do is draw another picture. Let's see. And in the place of the 3 and the 4, I'm going to put a single resistor equal to 1.71 ohms. All right, then we have our 1 ohm resistor here. Then in the place of the 2 and the 5, we can put a 1.43 ohm resistor. And we have just one current, the current I1. So we've already simplified it down to something that's really, really easy to deal with. We could simplify it further, but there's really no reason to. All we need to do is write a loop equation now. So I'm going to start here, go around clockwise, and write my loop equation. And what we're going to have is, again, starting here, walking along the loop. The first potential I hit is the potential of the battery, plus V. All right. When we move across here, we're going to change in potential by an amount IR. It's going to be a drop in potential. And I like to write these like the resistance first, 1.71 I1. And again, IR. It's a drop in potential because if we go from here to here, and again, look at my current direction, I've got the current moving to the right. Current always moves towards from higher to lower potential. So we keep walking along the circuit. When we get to here, we're going across another change in potential. It's going to be another drop in potential by an amount I1 times 1.43 ohms. When we go across here, we're going to drop in potential again by an amount I1 times 1, and we're back to where we started. So these have to add to 0. Right? So this equation is pretty easy to solve for I1. Keep in mind that this is 12 volts here. So this is going to read 12 volts minus, and I'm going to go ahead and just combine like terms here. We got 1.71, 0.43 plus 1. Okay, if I'd work this right, we've got 4.14 ohms times I1, go ahead, and then equals 0. I went ahead and put the units in. So I1 is going to equal 12 volts divided by 4.14 ohms. Okay. And I get about 2.9 amps. Oops. 2.9 amps. All right, so I1 is a known value now. All right. There's a lot of ways to go through I2. I'm going to go ahead and do this. Looking back at the original picture, and remember potentials. I'm going to go ahead and color code the potentials. Red, that's going to be good to there. Now there's going to be a drop in potential. So I'm going to color this one orange. For those of you who've seen me color code these potentials before, you've seen that I usually just kind of work through my little color wheel here. I'm going to give this potential a coat of green, and then black. All right, so the difference in colors represent differences in potential within my circuit. So we got black to red, which is a 12 volt potential. We got red to yellow, yellow to green, and then green to black. Well, if I do the same thing in this picture, let's see, this was red to here, then this would be orange to here. So if I knew the potential across here, red to yellow over here, or orange, that's the same potential. So if I know that potential, I can apply that potential here to calculate the current I2. So that potential is pretty easy to get. The difference in potential, the difference in potential from red to black here across that resistor is going to be the current, 2.9 amps, times the resistance, 1.71 ohms. And the product of the two is 4.96. Actually, I'm just going to approximate that. That's approximately 5 volts. So it's important to know that that is the potential difference, all right, between red and orange in that picture. So, as I look over here, red to orange, the potential across here also is 5 volts. So we can just apply Ohm's law to get the current I2. So Ohm's law is V equals IR, so we're going to have 5 volts is equal to I2 times 3 ohms. And if we solve that for I2, we get 5/3, which is, what is that, 1.67 amps, rounded to 3 sig figs. All right, so important points of this problem. One, you have to recognize that the original picture, has a bunch going on. I mean, it's got 5 different currents there. A good way to handle that, well, we can use the idea of equivalent resistance to, simplify this pair down, simplify this pair down. Anytime you calculate an equivalent, you should redraw the circuit. I really think you should even go so far as to move the color codes over to color code every part of every circuit that you draw. Now we've got this circuit down to 1 loop. You can keep going and write it 1 voltage with 1 resistor if you want. These are obviously in series, the 171, the 1.43, and the 1, but there's really no need. Once you get it down to 1 loop, just write a Kirchhoff's law equation. Sum of potential differences equals 0. In this case, we got the current, which allows us to calculate the voltage across here, which is the same as the voltage across here, which allows us to calculate the current I2. By the way, that voltage would be good here to calculate I3. If we wanted to, we could come here, calculate that voltage. It would be 1.43 times 2.9 amps, or 2.9 amps times 1.43 ohms. That would give us the voltage here. That's, whoops, and I kind of missed that. This is green on this side. That actually, in my color coding, should be green. If you were wondering earlier about that, did he miss that? The answer is yes. That's okay. All right, it didn't affect any of the work here anyway. So this yellow to green potential we would calculate by IR, 2.9 amps times 1.43 volts. We could then take that voltage and apply it here to get I4 and here to get I5. And we'd have this thing completely wrapped up. So anyway, I hope this video helped demonstrate how to use equivalent resistance to simplify a circuit down and kind of work the problem backwards. Everybody have a great day.